In this video, we will walk through the hardware wiring of a 4-bit shift register step by step. This connection is especially important because registers make up around 30% of a CPU. For example, this is the picture that I explained in one of the previous videos. I told you that we have many registers within the CPU, R1 and R2 and the memory address register and the instruction register. So we have a total of 7 elements or 7 units, 1, 2, 3, 4, 5, 6, 7. 4 of them, 1, 2, 3, 4 are registers. So you have to be able to connect the register in order to build around 30% of the CPU. And I am saying 30%, not 60% or more, because I cannot consider the control unit as one unit. It is equal to like 3 or 4 units. Okay, so let's start by showing the components that we need today. First of all, we need some wires. We need 4 LEDs, 4 resistors, and 4 switches. These are the inputs, these are the outputs, and these are a connection between the inputs and the IC. And finally, the IC itself, which has a number 47LS95. I hope that you can see this from here. Okay, so I am going to connect this here. But before that, I want to show you the switch circuit. Let's make some connections. I remember that I have the IC. This is the IC. And before explaining the switch circuits for the input and the LED circuits for the output, I just wanna take a look on the data sheet. We have here the name of the register. It is called 4-bit shift register, and we have its number, which is 74LS95B. And this is how the IC looks like, and these are some specs or specifications about the voltage, the current, and so on, but we do not need to look at this. We need to look at this, and this one. By the way, this is a graph of how this register looks like from inside. But I am not going to explain this because we already spent some time on explaining these basic logic gates. Let's start looking at this register. As you see, we have 14 pins. Pin number 14 is the VCC, like the previous logic gates. Pin number 7 is the ground. And then we have something called DS, CP2, CP1. Other than that, we have the inputs and the outputs. It is called 4-bit shift registers, which means we have 4 inputs and 4 outputs. By the way, this can work as serial and parallel, and I'm going to explain this from this part. The S pin, which is number 6 here, is called the mode control input. Why do we need a mode control input? Because I told you that we can make this IC work as serial or parallel, right? So you can use this pin to determine if it is gonna be parallel input, parallel output, or serial input and parallel output. And that's why it is called shift. Shift means the output should be shifted right or left, okay? But anyway, this is not our focus today. And then we have the DS, which is called serial data input. If you are going to use this as serial input, parallel output, then your input should be connected to pin number 1. If you are going to use parallel input, parallel output, your inputs must be connected to pins from 2 to 5. So because we are going to use parallel inputs, then we are going to connect this with the ground or the VCC. I'm going to explain the truth table to see how each one will be connected. Then P0 to P3 from here to here are the inputs, parallel data inputs. And then we have CP1, it is called serial clock. So again, if you are using serial input, then this is your clock. If you are going to use parallel inputs, then this is your clock. CP2 is the parallel clock, active low, going edge. So if to make this shift register work, which means taking the inputs and put them on the outputs, store them temporarily here and put them on the output, then you have to connect your clock on CP2, and CP2 will trigger the operation of the register on the low edge, not the high edge, which means not like this edge, but this edge. These are the input, these are the main pins, but we have also Q0 to Q3, which represent the parallel outputs. Let's now look at the truth table. We cannot explain the connections without explaining the truth table. First of all, we have operation mode called shift, and we do not need this in this video. And we have another modes like many things here, not change and undetermined, many things, but this is not our focus also. Our focus is the parallel load, okay? So if you are going to connect parallel inputs to take parallel outputs, then you need to look at this one only. Okay, that is easy. So let's see how each pin will be connected. If you look at S, it should be connected to H, because high means using parallel input mode. Low means using serial input mode. And you can see this for the shift mode, S has to be connected to the L or the low. For CP1, because CP1 is the clock pin for the serial inputs, then you can either connect this to 0 or 1, because usually CP1 is a clock, so it works only on the high edge or the low edge. But if you don't change, which means connecting continuously to the VCC or the ground, then CP1 will not make any changes, will not affect the operation of the register. Then CP2 is our clock for the parallel, and that's why we have to connect a clock here. Then the DS should be connected to the ground or VCC. It doesn't matter also, because this is the serial input, and if there is no clock on CP1, then there is nothing going to happen with the DS. For PN, it should be connected to PN, which means you should put your inputs here. And if you do this, if you connect the pins like this, then you will get the outputs, and the outputs are from P0 to P3. So Q0 will be equal to P0, Q3 will be equal to P3, and so on. Right? So do you understand now the truth table? What we need to do is to go to each pin and connect each pin as clarified here. These are the pins, and let's start with the S pin. It should be connected to high, so S pin should be connected to VCC. Then the CP1 should be connected, it is don't care, which means anyway you can connect this to the ground. CP2 should be connected to the clock. I'm going to leave this for now. DS should be connected also, it is don't care, so we can connect this to the ground. Sorry, let's make it like this. It doesn't matter if you make it in the upper part, but anyway. Okay, so this is the DS. Now we have the inputs. Sorry, this is also to the ground, and this is to the VCC. The remaining are the inputs and the outputs. So let's connect the inputs and the outputs. Do you remember how can we provide 0 or 1 to the inputs? By the switch circuit. We already explained the switch circuit many times. So I'm going to make something like this. This is our VCC, and we have 4 switches, and the second pin should be connected to resistor. I should have went down, but anyway, this is to the ground. Then P0 will be connected to this switch. P1 should be connected this switch. This should be connected to this switch, and finally this should be connected, oh, not correct, this should be connected here. For the output, we can see the output by connecting some LEDs. So I am going to connect some LEDs. This is our first LED, second LED, third LED, and the last one. And they should be all connected to the ground. I am not going to add a resistor here. We do not need it actually, but the perfect circuit should have the resistors. But in this case, we do not need it because we can directly connect the LED to these outputs. That is our connection. I am not going to say keep this in your mind or memorize these connections, but I'm going to take them one by one. So let's take pin number 1. This is our IC. So I just want to make something here before the connection. I just want to make sure that this, because I have these aligned here, so I'm going, this is pin 1, 2, 3, 4, 5. Okay, so I'm going to add this here, and then let's start. Let me zoom in a little bit. Okay, I think this is good. 1 second. Okay, now let's connect pin number 1 to the ground. And then pin number 6 to the VCC. So this is our VCC. Pin number 7 to the ground. Pin number 9 to the ground. This is 8 and then 9, so we need a bigger wire, a longer wire. So this is to the ground of pin number 9. Pin number 14 to the VCC. Pin number 14 to the VCC. I didn't explain how can we get a clock here, but it is very easy to just connect this to a switch circuit, VCC, switch, and then resistor and the ground. And when we click here off and on, when we turn the switch on and off, we provide a clock to this pin. So you can connect a real clock, or you can make a switch circuit and use the switch as a clock. So I'm going to make this connection. I have this switch, but I need another one here. So I am going to make this connection. So let's connect this pin to this pin here. What I am doing here is very important. I just want to tell you, we need to make a perfect circuit, and to do so you have to use wires with an appropriate length, right? So I connect the wire first, and then I connect the switch. Okay, so we need this switch on the one on the left, so I'm going to connect this left with the wire here. You can choose any one, by the way. And then this is the pin that we connected, the wire that we connected. We need to take the upper part from the switch to the VCC. I know that you already know this from our previous discussions, but in case anyone just started from this video, then he knows what to do. And then we need a resistor to the ground, so I am going to have this resistor here to the ground. Sometimes it takes time, but anyway, let's connect this side first and then this side. So we finished also the switch circuit. We need now to connect the input circuits. So we have a switch with we have a block with 4 switches, which is this one here, this one. We already connected the upper pins to the VCC. If you look at this part, we connected the 4 pins to the VCC. What we need to do is to just connect the 4 resistors to the ground. So we have 4 resistors here. First one to the ground. Yeah, we have these resistors. Second one to the ground. Third one. And I think, yeah, we need 4, so this is our last one. Oh, by the way, you can increase the speed of the video, but I'm explaining everything step by step, so I'm not going to increase the speed. Anyway, so what we need now is to just connect these 4 red wires. I'll start with this one. Okay, sorry, which one? Yeah. Let me show you practically. This is better. So we know that the binary starts from right to left, which means this is 0, then this is the next one, and the next one, and the next one. So we start from right to left. And we need to do the same here. Someone might connect 0 to 0, 1 to 1, but that is wrong. We need this. Our IC is like that, in the same direction like this one. So we are considering this like bit 0, bit 1, bit 2, and bit 3. But if you look at the numbering of the IC itself, it's saying P0, P1, P2, P3. But this is not what we need. The pin on the first pin on the right is we need to consider it as, I mean, like the base 0, and this is base 1, and this is base 2, and this is base 3. If you remember, if you say 1 0 1 1, this is considered with a weight of 2 to the power of 0 to 1 to 2 to 3. So this is our first bit on the right. So this should be our first bit, not the 4th one. I hope that you understand this. So I'm going to connect this pin to number 5. You might wonder why number 5. I'm going to show you again. I like to show this picture many times. We connect the first switch on the right to the first pin on the right, and this is pin number 5. Then we are connecting 4, 3, 2, and so on. So this is the next one from number 4 to the next one here, and then number 3 to the next one here, and finally pin number 2 here to the last switch, the one on the left. Now we finished the inputs. Let's connect the outputs. We should connect leads from these pins to the ground. So I have already the 4 leads here. As I said, the large part inside is the ground, so let's start with this pin to the ground. Again, this pin is pin number 10 to pin number 13. Sometimes the camera is not showing, so I have to make like this. Pin number 10 to pin number 13. So the ground is the big one. The ground is okay. Now we have everything is connected. We have to connect the power supply. I hope that you remember our power supply, but I am going to show you quickly. So let's connect the power. This is our power supply and it provides 5 volts. Now we need to connect the green one to VCC and the blue one to the ground. As you see, it works, but it is not working correctly. Why? We have here 1, 1, 1, 0. So we should see 1, 1, 1, 0. The reason for that is we didn't click on the clock. We didn't provide the clock. This is our clock, and we should make like this, and it should now works fine. As you see, it should work fine. So we have on, and off. Let's make it like off 0, 1, 1, 0. So, but it is not working yet because we need to provide a low value. By the way, when we turn the switch on, we moved from low to high, which means high edge, but it is not gonna work. It is gonna work on the low edge. When you turn the switch off, that means you are moving from high to low, and this is the low edge. Let me show you. Do you see it? Now let's try 0, 0, 1. Okay, let's try 0, 0, 0. It works. Let's try 4 1s. It works fine. Okay, so now you know how to connect 30% of the components within the CPU, as I explained at the beginning of this video. What we need to do now is to connect. This is what we explained today is R1. I am going to connect R2, but I am not going to make another video for R2 because it is exactly the same one like this. And then I'll put like, let's say this is R1, maybe R2 here, and the arithmetic and logic unit should be here. So I'll make this offline, R2, and then I'll show you how to connect R1 and R2 with the ALU. That is very important. And once we do this, I think we can move to the next step, which is how we connect them through a data bus like this one. So connect this connection and this connection, and then we can see the output by some LEDs, and we can put some switches here and test this circuit alone. Once you can do this, then you can connect these two registers to the bus and the output to the bus and try to move data between them. That's all we need to do in the next step, and that's all for today, and see you in the next video.